Hello everybody, I am Bhikshamaya Chalakani, Assistant Professor of Physics from Government Degree College, Rumen, Nalgonda. Today I am going to explain the 2D lattice and 3D lattice in this lecture. So we see. So lattice types. There are two types of lattices. Plane lattice, that is 2D lattice, and space lattice, that is three-dimensional lattice. So in the first lecture we have seen how the lattice points are in 2D and 3D, and we have studied about unit cells and primitive unit cells, just like that. Now Bravais lattice, it is a common phrase for distinct lattice type. So that means a particular lattice type, or we can say a unit cell. So by repetition of that unit cell or that particular lattice in three directions along the basis vectors, it should fill the entire space or entire plane. Okay. So similarly, that one, the distinct lattice. Okay. If one lattice is varying from another lattice, if at all there is a change in lattice from another lattice, we say that it is a distinct lattice from another lattice. So such a distinct lattice, another name is called a Bravais lattice. So distinct means it varies from one lattice to another lattice. So the Bravais lattice looks exactly the same no matter from which point in the lattice one views it. So lattice in space is the three-dimensional thing or three-dimensional object. In the 3D, the total lattice points are filled. Whatever the point you take as reference, whatever, so what is the environment you are observing, or what is the uh, shape of the unit cell or surrounding. So same you observe at another lattice point. Okay. So therefore, the Bravais lattice or the unit cell, if you take one lattice point as origin and there you see the unit cell, you are having particular structure, let us say, with respect to another point also. So around the nearest environment, you observe the same unit cell with the same structure. Okay? So that is the Bravais lattice looks exactly the same no matter from which point in the lattice one views it. Okay. From wherever we see, we observe the same Bravais lattice. Now 2D lattices. 2D lattices. So it is generated with a repetition of lattice points along two basis vectors. Okay. So here I am showing here. Okay. Here it is. So here one lattice point we keep, and one more lattice point here. So So this is along x-axis. If we keep another lattice point at the same distance, here we will have lattice point. Similarly, so it is along y-axis. Here one lattice point is there. If we translate the vector along the same direction, we translate the basis vector along the same direction, we will have one more lattice here, just like that. So similarly, a parallel lattice vector, if we translate just like this, here we get the one more lattice point. So in that way, so in any direction, in this direction we translate by a distance, in this direction we translate by b distance. So in order to get this point, we can say that this point is translated along y direction by b distance. Okay, just like that. In other words, whatever the lattice point exists here, that is translated along x direction by a amount. Okay, so in that way, by translating or by repeatedly pointing out the lattice points at the ends of basis vector, we get 2D lattice. So they are infinite lattice in 2 dimensions if there is no restriction on lattice parameters. So that means, so here the lattice parameters are A is one parameter and B is another parameter and alpha is the angle. That is also one parameter. So in two-dimensional lattice, there are three lattice parameters. Okay, if we do not keep any restriction on these three lattice parameters, we get infinite lattices. That means infinite unit cells also. So what are the restriction or conditions we are imposing? That means, so infinite means, so let us say it is one unit cell, let us say something. Okay, it is one unit cell. So here the angle is something. So if we do not keep any restriction, if we do not keep any restriction on angle for this, so for this angle, for this angle, we get one more lattice or unit cell. Okay, for other angle also we get one more. So okay, for another angle we get one more lattice. That means it is A. By keeping B as same, so that is another lattice. So for different angles we get different unit cells, and for different lengths of A and B we get different unit cells or lattices, Bravais lattices we can say. So in that way we get infinite lattices. Okay, we get infinite lattices. So for that reason, so we are imposing the conditions on the lattice parameters that gives us the conditions on lattice parameters gives us different lattices or different geometrical shapes we get. So if I keep the condition, so any two sides, so here I am getting, I expected to draw second figure. So if we impose a condition, any two sides, that means opposite sides are equal. So if we fix the angle, not at all that, Only we have only three lattice parameters. If we fix the angle, particular angle, and A and B are not equal, for that fixed angle, we are getting this type of shape. We can say it as parallelogram. Parallelogram. Okay. So that is one lattice type. That is one lattice type. So we can also call it as oblique lattice. Oblique lattice. Similarly, if we impose the condition for the same parallelogram by taking a parallelogram, in that parallelogram, if we fix the angle to 90 degree, we get the rectangle. Rectangle. Okay. So it is another lattice type, or it is another geometrical shape. So that is one unit cell. We can say, or it is one system. Okay. So here one symmetry is existing. Similarly, if we equate A is equal to B, A is equal to B, we get a square. So we get a square. That is another lattice type. Okay. So that is another geometrical shape. Okay. Next, rhombus. Rhombus is there. Okay. These are the, let us see. An oblique lattice is invariant only under the rotation about any lattice point for n is equal to 1 and 2. So in case of yesterday we have seen, or in the last class we have seen that rotation. So lattices, there exists rotation symmetry for n is equal to 2, 3, 4 and 4, 6. But in case of 2D here, oblique lattice, that means a parallelogram. You can say a parallelogram lattice is invariant only under the rotation theta is equal to 360 and theta is equal to 180. Theta is equal to 360, obviously any object, for any objects there exists symmetry or invariant structure. So for theta is equal to 180 also it exists. So only these two possibilities are there, but for 3D we have studied, okay. So n is equal to 3, 4, 6. For n is equal to 3, 4, 6 also rotational symmetry exists. So we can achieve these symmetries. So by imposing suitable conditions on A, B and theta. Okay. So in that way we get other shapes also, other geometrical shapes. So we see next these symmetry elements. So by putting the different conditions, we are getting those are the symmetry elements. Okay, for each corresponding n, we get some one operation, symmetry operation, or corresponding rotational axis. So these, there are symmetry elements also. For corresponding each operation, there is symmetry element. These symmetry elements in turn put the restrictions on the shape of the lattice. Okay, that's what I said. So that gives us the shape of the unit cell. Okay. The heart of the classification of lattice is the symmetry of the lattice. So the classification of lattice is based on the symmetry of the lattice. Okay. There are five distinct 2D lattices. If we see how many distinct lattices are there, there are five. So distinct lattices, those are called as Bravais lattices. There are 5 Bravais lattices. We can also call them as unit cells, different unit cells. So a square, if A is equal to, these are the lattice parameters in 2D, these are the conditions imposed. A is equal to B and alpha is equal to 90. We get a square shape. This is the geometrical shape of the lattice. That means 4 lattice points at the corners of a square. Okay, that is one geometrical structure and one lattice. So another case, alpha is equal to 90 but not A is equal to B. So that gives us rectangle. So that is one another type of lattice. So another one is centered rectangle. So in the rectangle, at the center of the rectangle, one more lattice point is located. So then that is called centered rectangle. So here it should be, A should not be equal to B. Here it should not be. Okay. Centered rectangle. 120-degree rhombus or hexagon. So another lattice, if alpha is equal to 120, for above 3 cases, alpha is equal to 90. So if alpha is equal to 120, so that is hexagonal shape or hexagon. One hexagon is equivalent to 3 120-degree rhombus. Okay, we see in the next picture. So we can say the lattice type has hexagonal or 120-degree rhombus. So it is another lattice type, and parallelogram or oblique lattice. So it is also called as general lattice. So here A not equal to B, alpha is also a general value. So that is parallelogram, a general lattice or oblique lattice. Okay. So from this, it is clear that so there are 5 Bravais lattices exist. There are 5 Bravais lattices are there in 2D. So we can say there are 5 unit cells also. So we have to remember the crystal systems are different. The crystal systems are different. That means, so the crystal systems are defined according geometrical symmetry. According the geometrical symmetry only, the crystal systems are defined. But Bravais lattices are not according the geometrical symmetry. Not only according on geometrical symmetry. So that also based on lattice points or which type of lattice. If we rotate the if we uh, fill up the total plane with which type of lattice we get, that lattice is called Bravais lattice. So here you will be getting clear idea. So crystal geometrical symmetry or geometrical shapes. That means square is one geometrical shape, a rectangle is another geometrical shape, and rhombus is another geometrical shape, and parallelogram is another geometrical shape. But centered rectangle, so even though it is center rectangle, nothing but it is a rectangle. According geometrical shape, it is a rectangle. At the center of the rectangle, lattice point is located. Therefore, the center rectangle also belongs to the family of rectangle. Okay, that means the geometrical shape of the centered rectangle is again a rectangle. Therefore, according that, so there are four crystal systems in 2D and five Bravais lattices in 2D. So we see next. So here I am illustrating. So the geometrical shape of the simple rectangle is, so this one total what we are observing here. But centered rectangle is the same thing with additional point at the center. So the geometrical shape of the rectangular lattice is rectangle, and the geometrical shape of the centered rectangle is again a rectangle. So therefore, these two comes into the same crystal system, that is rectangular crystal system in 2D. Therefore, there are four crystal systems in 2D and five lattices or five Bravais lattices or five unit cells, different unit cells in the 2D, two-dimensional lattice. Right. So we are seeing. So with this rectangular lattice, we can fill the total plane. Now you can see. You can see. Okay, no problem. Right. Now rhombus, hexagon shape. So that means this one. Okay. Here also. And right. So it is the rectangular center rectangle. With this we can fill the total plane. Now you can see, check also, just like this. Again, here we are forming another, we are filling the lattice with the same shape or geometrical lattice point in vertical place also. So just like this. So in that way, so with the same shape, that is unit cell, we are filling the total lattice in plane. Okay. So therefore, the centered rectangle is one unit cell. Now we are seeing 120-degree rhombus or hexagon. So here we are seeing. So it is hexagon shape, but it is a combination of three rhombuses. Okay, it is one rhombus and it is another and it is three, third one. So in that way, with this shape also, for this type of lattice, so with this geometrical shape, we can fill the total lattice. Okay, so so it is another lattice in 2D. Now we see the next. So here the angle is identified. This angle is 120 and opposite angle also 120 generally. So if it is 120, similarly this one also 120. So 240 in 360, 120 is there. That means these angles are 60 and this angle is 60 and here this angle will also be 60. Okay, just like that. So we call it as hexagon or 120-degree rhombus. So if we see the effective number of lattice points for all these unit cells. So for a square, so okay, for a square, four lattice points at four corners, and that gives us one lattice point. For rectangle also, so for rectangle also four, it is centered rectangle, but I am talking about rectangle. There we do not have the center point. So we have 4 lattice points at 4 corners. So again, the number of lattice points for a rectangular unit cell is again 1. In case of centered rectangle, so we are having one more point at the center of the rectangle. It is not being shared by any other rectangle. Therefore, the number of lattice points for centered rectangle is 2. Is 2. And similarly, the number of lattice points for parallelogram or oblique lattice is also 1. And in case of this lattice hexagon, so the center point is totally confined to this unit cell or hexagon. So its contribution is 100%, is one lattice point, and the corner point, the contribution of corner lattice point is so 1 by 3. 1 by 3. There are such 6 points are there. There are such 6 points. So how do we know that its contribution is 1 by 3? Now we can see here. So if we see this lattice point, so that what I want to say, one corner of the rhombus, one corner of the rhombus. It is one corner of the rhombus, right? So this one corner of the rhombus is being shared by three rhombus. So similarly, so the corner point, it is also a corner of the rhombus. Therefore, its contribution to this is 1 by 3, and such 6 points are there. 6 into 1 by 3 gives us 2. 2 plus this center one. We are talking about hexagon, not a rhombus, but for this one also, you can feel how many hexagons touch this lattice point. In order to know the contribution of one lattice point to uh, to this hexagon, we have to fill the total planes around this lattice point. So 3 hexagons will touch this corner point. Therefore, its contribution is 1 by 3 to a particular hexagon. Then 6 into 1 by 3 gives us 2 plus 1, 3. Totally, the effective number of lattice points for a hexagon in 2D is 3 points. 3 points. Now we see next one. So here we are seeing it is lattice, that means Bravais lattice, you can say, or a unit cell. So it is a crystal system. So for the centered rectangle lattice also, the crystal system is same, rectangle and rhombus. So these are clear, and you know these conditions on parameters also, right? So we are seeing here now. So 3D lattice, 3D lattice, three-dimensional lattice can be generated with 3 basis vectors. We know this. So there are infinite lattices in 3 dimensions also if we do not impose any conditions on lattice parameters. The 3 basis vectors are A, B, C, A bar, B bar, and C bar. And the angles among them is alpha, beta, gamma, as shown here, alpha, beta, gamma. So now we are having 6 lattice parameters. So A, B, C, and alpha, beta, gamma. So all these parameters may not be independent. So we can impose some conditions on them. We see the different lattices in 3D. So So it is general. A is not equal to B, not equal to C, and B and C also not equal. Similarly, there is no relation among these three angles also. So it is totally, however, the oblique lattice in 2D, we can say it one also general lattice in 3D now. So here, by imposing the conditions, so it is the simplest structure. If A is equal to B is equal to C and all angles are equal, that is equal to 90. So in that case, we get cube. So next one, tetragonal. A is equal to B is equal to C and the angles are equal, that equal to 90. Here we are getting tetragonal. So that means a square prism, that also called as square prism. So that means if we keep all squares one over another, if you keep on placing one square above another square, that forms this tetragonal. Okay, and orthorhombic, the edges are not equal but angles are equal, so rectangular prism are orthorhombic. So that here, okay, okay, no problem. Next, uh, hexagonal. Hexagonal. These are the conditions imposed. And parallelopipe or equilateral or equiangular. So it is also called as trigonal. Trigonal. These are the conditions imposed. A is equal to B is equal to C, and alpha is equal to beta is equal to gamma, but not 90. And monoclinic. The sides are not equal. Two angles are equal to 90. The third angle is not equal to 90. And seventh one, it is triclinic. So it is general. It is analogous to parallelogram in 2D. And in 3D, it is called as parallelopipe general lattice. So where we called oblique lattice, here we are calling it as triclinic. And sides are not equal, angles are not equal. So if we see the geometrical shapes, they are in they are as shown in figure. Okay, so here, so P is primitive, that means uh, corners, lattice points at corners. Okay, the lattice points at corners only. So I is body centered. That means at the point of intersection of body diagonals. Okay, so that is body center. And F is the face centered. So that means, in addition, in case of body centered cubic, so we have 8 lattice points at 8 corner points, and in addition to those, one point at body center. So in case of FCC, 8 corner points, 8 lattice points at 8 corners, and 6 lattice points at each face center. That means corresponding each face center, 1 lattice points. So there are 6 faces and 6 lattice points at face centers. So they their contribution to unit cell is 3, and the 8 corner points contribution is 1. Totally for FCC lattice, effective number of lattice points is 4. So C is the side centered or end centered cubic, but in this cubic structure, it is not present. Okay, only these three we are having. So here we can say cubic uh, cubic structure, cubic lattice. We call it as cubic lattice or cubic Bravais lattice. And the shape of the geometrical shape of the cubic lattice is a cube, geometrical shape. Okay. So in Bravais lattice, there are geometrical shape is same, but according the location of lattice points, there are three lattices, different lattices. Geometrical shape is same, but the lattices are different. The lattice points are located in different positions. So therefore, there exist three Bravais lattices. So similarly, we see the next one, tetragonal. So here primitive is there and body centered is there. Okay, here we are having two Bravais lattices. And third one, rectangular prism. So orthorhombic system. Here we are having four Bravais lattices. So in addition to the first three and C, that one is side centered or end centered. That means we have one point here. So we have one point here at this point and one point here, just like that. Okay. So end centered. So since these points are located along C axis, so we write the C. Okay. So if the end centered points are located along B direction, so we write here capital B. So if the end centered points are located along A axis, we write here capital A. So just like that. Anyway, they are end centered points. That means on opposite faces, two opposite faces only. So it is hexagonal and 120-degree rhombus. So that means in 2D we have seen this hexagon shape. If we keep on placing such hexagons one over another, we can build the 3D object. So that is just like this. And again it is a combination of these such this type of cubes. Okay, three such cubes form. It is not exactly cube. We call we will discuss in the next slide. So it is hexagonal shape. Okay, 120-degree rhombic prism. Generally, 120-degree rhombus is a 2D object, and in 3D we call it as prism. Okay, here also we have only primitive only, no other lattices. Okay, here monoclinic or parallelogram prism. So here two angles are 90, but not the third angle, and the sides are also not equal. So therefore, here we have shown here primitive lattice exists. That means at corner points lattices and end-centered lattice. End-centered lattice exists in this case. So it is a general one, parallelopipe. So so here we have only one lattice only, no other. The primitive only. If the symmetry increases, the lattices increases, but it is not symmetrical one. So symmetry decreases in this case. Therefore, only primitive we are having. Okay. So these are the seven crystal systems, and the seven crystal systems according their geometrical shape or geometrical symmetry, but according lattice points, the location of lattice points, there are different Bravais lattices we have seen. The total they are 14. Now here observing, okay, in cubic crystal system, the shape of the unit cell is cube. Okay, we have discussed this. Here, primitive, body centered, face centered, so just like that. And tetragonal. If we count these right marks, 3, 2, 5 plus 4, 9, and it is 10, and these are 4, 14. Totally, we have 14 Bravais lattices. So they are divided into 7 crystals. That means, so we are not dividing the Bravais lattices into 7, but according their geometrical shape, at first they are classified. After that, and in addition to primitive, there are different lattices. Okay, in that way, there are 14 Bravais lattices and 7 crystal systems. So here I am stopping. Okay, what we recapitulate it. Okay, so in this lecture, we have discussed types of lattices. That means basically, broadly speaking, 2D lattice and 3D lattice exist. In 2D lattice, there are 4 crystal systems and 5 Bravais lattices. The 4 crystal systems are square, rectangle, centered rectangle, and rhombus or hexagonal. That is third one, and fourth crystal system is parallelogram. And the 5 Bravais lattices are square Bravais lattice, rectangular Bravais lattice, and centered rectangle Bravais lattice, the rhombus lattice, and parallelogram lattice or oblique lattice. Okay, and in 3D there are 7 crystal systems: cubic, tetragonal, orthorhombic, hexagonal, trigonal, monoclinic, and triclinic. And there are 14 Bravais lattices out of these 7. Okay, so we have discussed these things. Thank you very much for watching.